the tiny gears that built the digital world and why they suddenly disappeared. This is a story about forgotten precision before silicon chips, before circuit boards, and definitely before the glow of a screen in every pocket. There were gears. In the 19th century, across Europe and America, master craftsmen were building machines so small and so precise they bordered on the unbelievable. Watchmakers in Switzerland, instrument engineers in Britain, scientific toolmakers in France, tiny springs, microscopic screws, gear trains assembled by hand under magnification. This was micromechanics, and it quietly trained humanity to master the miniature. Chapter 1. Thinking small. In places like Geneva and the Swiss Jura Mountains, watchmakers weren't just building timepieces, they were solving problems of friction, tolerance, and material fatigue at scales most people couldn't even see. A mechanical watch contains dozens, sometimes hundreds of components working in harmony. Every tooth on every gear had to be cut perfectly. Every pivot had to rotate with almost no resistance. Every spring had to store and release energy with precision. This wasn't decoration. It was engineering at the edge of what human hands could achieve. And it created something profound, a culture obsessed with precision. Chapter 2. The industrial mindset of Alvis micromechanics didn't stay inside watches. The same precision principles moved into marine chronometers for navigation, scientific microscopes, surveying equipment, early telegraph mechanisms. The world was shrinking geographically and technologically, and then came electricity, transistors, vacuum tubes, integrated circuits. The skill of controlling tiny moving parts became the skill of controlling tiny flows of electrons. Mechanical tolerances turned into electrical tolerances. Springs became semiconductor junctions. Gears became logic gates. It wasn't a clean break. It was an evolution, or at least it appeared that way. Chapter 3. The sudden silence. Here is where things get interesting. For nearly a century, micromechanical craftsmanship dominated precision technology, and then almost everywhere at once, it faded. By the mid-20th century, the global focus had shifted. Factories that once refined microgears pivoted. Research funding flowed toward electronics. Mechanical miniaturization slowed dramatically outside niche industries. It wasn't gradual in spirit. It felt decisive, as if the world collectively agreed. Mechanical precision has reached its limit. But why? Was it simply economics? Electronics were faster, cheaper, scalable. Was it physics? Electrons moved faster than springs, or was it strategic? When transistor research accelerated after World War II, investment became concentrated, coordinated, and nationalized in some regions. Mechanical microengineering, once the frontier, became legacy craft. The shift was global, almost synchronized. Chapter 4. Coincidence or inevitability. Now, we need to be careful here. There is no proven conspiracy. There's no document saying, stop building gears, build silicon instead. But history shows moments where industries pivot with unusual coordination. The question isn't whether electronics were superior. They were. The question is, why did mechanical microengineering plateau so suddenly across nations that previously competed fiercely? Why did no major power double down on extreme mechanical miniaturization as a rival path? Could we have seen an alternate technological world, ultra-advanced mechanical computing, hyper-refined kinetic logic machines, clockwork processors? It sounds absurd now, but so did billions of transistors in your pocket once. Chapter 5. The foundation still remains. Here's the twist. Even if micromechanics stopped being the frontier, it never truly disappeared. The mindset survived. Cleanroom engineers chasing nanometer tolerances are spiritual descendants of watchmakers filing gear teeth under candlelight. Semiconductor fabrication demands the same obsession: precision, material behavior, control at microscopic scale. Modern nanotechnology, manipulating structures measured in billions of a meter, rests on centuries of learning how to control the small. Without micromechanics, there is no microchip. Without watchmakers, there is no nanotech lab. What have we learned from this then? History tends to highlight breakthroughs, but it often forgets foundations. The digital age feels like a sudden leap. In reality, it may have been the final step in a process that began with ticking springs and brass gears. And whether the shift from mechanics to electronics was purely inevitable, or quietly accelerated by strategic forces, one thing is certain: the digital world was not born in silicon, it was born in steel, ticking in the dark.